This blue line down here is ground level at Mount Canigou. So you can see that this much of the mountain is obscured by water. It's almost like there's some sort of bulge there.
So you heard it here first. All you Globers out there denying the hump, one of your top guys just explicitly told you there is a hump there. And why are you calling that ground level? Isn't that ground level at Canigou also, Roof? And that one? Aren't these all ground level at Canigou? Why the blue one, bud? Oh yeah, because of hump, right? So what I found is that to get to the bottom of Ruhif logic is to go over the numbers he doesn't analyze and bring up. So let's look at them. So what does Ruhif have to do to achieve this quote unquote hump? He has to drop the horizon down almost 5 kilometers. That's what they have to do. That's over twice as much refraction that the flat earth observation would have it at. Ruhif claims that blue line is the bottom of Canigou, and that's where it should be on a flat earth. He's got it at 0.66, basically 0.67 degrees. Let me show you how perspective works, Ruhif, and why your measurements wouldn't work in reality. If we just call these clouds about 2 miles high, so you see that's 2 miles there. As we get closer to the mountain, the clouds drop down, that's 2 miles, and all the way off in the distance is also 2 miles. So let's say this cloud right here is sitting on the horizon. That's about how high it would be, 2 miles or around 2.7 kilometers. Let's see how Ruhif's math matches reality. So we put in a 60-kilometer horizon and a 2.7 kilometer cloud height, and we get 2.5 degrees. So let's see how high this cloud would be at the horizon. We literally have to shrink the screen down to a miniature, and the cloud would be that high it's sitting over the horizon. Does that match reality? No, I don't think so. I guess Ruhif thinks the mountain's shaped like this, but that blue line at the bottom he's saying is the ground level for Canigou. I guess he's saying that should be a flat earth horizon. But you can't have it both ways, Ruhif. So he wants it both ways, and I'm going to show you how. Okay, we'll even give him the benefit of the doubt and use the refracted value. So we know the angular size of the sun is 0.53 degrees roughly, and the globe calculated drop to the horizon is 0.67 degrees. So the true horizon has to be either globe or flat horizon. So if it's a globe horizon, let's just say that line in the middle marking the true horizon is a globe horizon, then the flat earth horizon would have to be way up here. It'd have to be off the screen. I literally had to lower the screen to get it to even fit. And if we claim that the true horizon is a flat earth horizon, then the globe horizon would have to be off the screen down there at the bottom. That's 0.67 degrees. So you can't have a flat and a globe horizon down there. You can't have a flat earth horizon up above the true horizon and say that it should be below. Ruhif, which is it? So using globe mass, these horizon adjustments are ridiculous. The answer is it's neither. The globe Earth mass is wrong. Let's look at some other measurements. So from here to here is 0.53 degrees in angular size, which at that distance makes 2.7 kilometers. We know the globe mass say that this line is 69 miles to the horizon, which makes this line 200 miles. And all this while this line is 2.7 kilometers. So take a look at that and let it sink in for a minute. So it kind of looks like that yellow and don't belong, right? Well, this gets way worse. Okay, so it says that Canigou is about 50 kilometers from the sea. Okay, and the globe maps say it's about 69 kilometers to the horizon. So we got 69 kilometers to the horizon. And from this little line, from the mountain to the land, is 50 kilometers, which makes this little line 150 kilometers. Are you kidding me?
Those hills are actually 500 meters above sea level. And that's not possible on a flat Earth. This image is completely impossible on a flat Earth.
Refraction in the air makes distant things appear slightly higher.
Look at that backdrop right there, and look at its distance from the horizon. Now imagine that that top line is the top of a mountain, or the bottom of a cloud, and the bottom line is basically the horizon. Okay, watch what happens when he lowers the camera and enters into the denser gradient. Look at the horizon and the top of the mountain or the bottom of the clouds. Look at the gap. As he gets lower, he's still line of sight, and look how it starts dropping down. So things in the distance are appearing lower, not higher.
whatever the effect is, it absolutely lowers it in the background. The density lowers that object in the background. And Miles Davis, who's put all those videos out of Trepane law, saying that there's a mountain in the distance and it's lower in perspective than it should be. And I've lined myself up at 210 meters, and then in the background we have this mountain that's lower than it should be. Well, here's your answer on a flat plane, Miles Davis. Here's your answer. Here's every glober's answer.
So the bottom line represents the horizon and the top line represents the cloud. Watch as he lowers the camera into the density.
Sure, the image from behind.
Sugar's thickest at the bottom. Look at the steeple or the cloud lower, not rise.
You can see
an object is getting lower down to the horizon, not raising up. So that's three completely different setups, all showing distant objects lowering due to refraction, not rising.